0, -1. All right, hi, welcome back to Math 234, multivariable calculus. I am still your host, Steve Dragoo. Today, we've got the second half of section 14.7. Uh, so, yeah, what did we do last time? Just as a quick reminder for ourselves. We were looking at local minimum and maximum values of 3D functions. So we've said we should first find our critical points, which means that both our x and y partial derivatives have to be 0 at the same time. And as long as we add one of those critical points, we can figure out if it's a local maximum or minimum by checking the concavity of our graph. If it's concave down, it's maximum. If it's concave up, it's a minimum. We had this super fun second derivative test right here. We have to look at three different types of second derivatives all at once. But as long as we found that the x and y concavities matched each other, we probably could find the local maximum or minimum. So that was last time. Now it's this time. Where we're going to, again, upgrade one of our ideas from Calc 1 to have it work for Calc 3. In particular, we're going to be looking at absolute maximums and minimums. And in order to do that, we need to be on a closed and bounded set. So let's start talking about that. And also, wow, this dumb thing is right in the way of the only button I wanted to click on. So let's expand this up here. Also, you might notice the bar at the top of the screen telling me to update OneNote has finally gone away because I did update it. So now I'm on the new version and there are going to be some growing pains. So bear with me while I figure that out over the next few days. In particular, the new version has gotten rid of my eraser button. So it's going to be a bit rough for a bit as I have to figure out how to erase things. But that's a me problem. Sorry that you have to deal with it too. So, again, we need to be on a closed and bounded set. A closed set is one where we're including all of our boundary points. So if I come over here and just look at this quick sketch of a region, the highlighted green spot is my region, that purple line is my boundaries. And again, in order to be a closed set, I need to be including all of the points on my boundary in my set. So I can't have any gaps in there. I can't, for some reason, have an unclosed edge. Can't have an open set. If I want absolute maximums and minimums, I need to be closed. Boundary points must be included. The other requirement here is that I need to have a bounded set, which effectively just means that I don't end up containing an infinite point somewhere in my region. So none of my points are going up to positive infinity and none of my points are going down to negative infinity, because if I had one of those, I couldn't have an absolute maximum or minimum, because I could always find a larger point, right? From going up to infinity, as soon as I pick one, I could then find a larger point. So I can't have that, must be closed and bounded. And then after establishing that, we're basically only going to look at closed and bounded sets when we do these maximum and minimum type problems. So the couple of steps that we would bring up from Calc 1. Oh no, what's happening? Okay, there we go. Everything's fine. Stepping up our ideas from Calc 1, the way that we did those absolute maximum and minimum problems would be we took a derivative, set it equal to 0 to find our critical points, which might show up as local maximums and minimums. And then also we'd be on some fixed interval. And so we'd also have to check our endpoints. And that was our process back in Calc 1. Check the critical points, check the endpoints. The largest among them is the maximum, and the smallest among them is the minimum. That was our grand plan. So we're going to need to do the same thing now in multivariable calculus, but of course that means we have to add extra steps. So we can't just do it an easy way, because why would that wouldn't be any fun? So the first step is still going to work very much the same. We're just going to find our critical points. Stage one, take derivatives, set them equal to 0. We'll find our critical points. We're going to test those. It ends up being the boundary values where most of the complexity with these problems comes in. Because now instead of just having 2 endpoints of whatever our region is, we're going to have an entire boundary curve that contains our entire region. Which means after we do the Calc 3 problem of finding local maximums and minimums, which involve 2 partial derivatives that both have to be 0, we then have to parameterize our boundary curve, perform a Calc 1 maximum and minimum problem on that boundary curve, which means taking a derivative of it, setting it equal to 0. But now it's a curve, so it should only have one parameter, meaning it's back to just a regular calculus 1 type problem. And then also that boundary should have some end values as well, some kind of boundary point that we're still going to have to check. So really, these absolute maximum and minimum problems are going to just contain an old Calc 1 problem, but also have extra steps on top of it. So that's my plan. That's what we're going to do. For the rest of today is just do a few of those types of examples, and come on. Don't erase that. I just wanted you to scroll. Is that so hard? Yes, it is so hard. It's so hard. We can't just scroll the page. Sorry, I'm fine. I'm fine. Setting just likes to turn itself on for no reason. Okay. Scroll. There we go. Again, just a rough outline of the kind of problem that we're going to do. Finding the maximum and minimums on this example right here. I'll do this Calc 3 step, which is finding critical points within the region itself, which is taking the 2 partial derivatives and setting them both equal to 0. I get not a ton of new stuff here because my function's just x plus y. Both its derivatives are 1. It will have no interior critical points because there's nothing that solves those derivatives equal to 0. Then my region D is the shaded gray region there on the inside of that parabola. So my boundary is made up of 2 separate curves, the green one and the blue one. Y equals 3 and y equals x squared minus 1. Those are my 2 boundary curves. So I have to parameterize both of those boundaries, meaning I'm going to get a function of a single variable or a single parameter, and then I have to take derivatives of those things too. So you can see I've color-coded them to have the blue curve and the green curve. The blue curve just has y being 3. I plug that in, and then again, take a derivative, set it equal to 0, but again, come up with no critical points. And for the green curve, now y is x squared minus 1, so I just make that substitution. Note specifically, because these are parameterizations, I am including bounds for my variable. That's going to be pretty important. More on that in a bit. But same thing, take a derivative, set it equal to this to 0, blah, blah, blah. This time I finally found myself a critical point. I got it at x equals -1/2. And then because I'm on the boundary curve, I should just come back to that boundary equation to figure out my y value. So in particular, I can see that I have that point at about right here. Right, that'd be my critical point. The one that's on the boundary, because now we're going to have 2 different types of critical points. We'll have our interior critical points, and we'll have our boundary critical points. But the final step to figure out our maximums and minimums is to go plug all this stuff in. So I only found the 1 critical point. It was on the boundary, so I plugged that in, -1/2, -3/4. So that's my single critical point that I have to test. But I also have to make sure to test all of my boundary points. In this case, both of my boundary curves were bounded by x being between -2 and 2. All right, I can even see that they're still on the screen. X must be between -2 and 2. But coming back up to the curve, I can see those 2 points of intersection where my 2 boundary curves meet. So I have to check those points. And notice that I solve for the points by just setting the 2 equal to each other. I want the intersection of 2 different lines. So set them equal, solve for x. I got that x is plus or minus 2. So I have to check those points as well. And then the last step is the easiest among them, hopefully, depending on how good you are with numbers. The largest value is the maximum, and the smallest value is the minimum. Cool, cool. So that said, let's go do a problem together. So find the absolute maximum minimum of the function x squared minus 2xy plus 2y on the rectangle x between 0 and 3, y between 0 and 2. So let's go maybe draw ourselves that rectangle. Yeah. And right away, I'm just going to pick out my boundary points because I can see them on my shape. I'm going to have 4 of them, each of the vertices of this rectangle. When I get to my final step, I'll need to check all of them. They are the points 0, 0. I don't like that pop up, but I'm sure it's fine. This one, yep, that's okay. One second, my pen's run out of ink. How does an electronic pen run out of ink, you ask? Yeah, I don't know either. Okay, it's back. Right, my eraser is gone. So let's go. Everything's fine. Everything's fine. Situation normal. Okay, that one's 3, 0. This one is 3, 2. And this one is 0, 2. And then why don't we move 0, 0? Just kind of pull it over there. Okay, so those are my 4 boundary points. I'll check them later. The first thing that we really want to have are a couple of derivatives. In particular, we want those derivatives to be equal to 0. So I'll have f partial x is equal to, that looks like 2x minus 2y. And it's going to be equal to 0. And then I'll go look at a y partial as well. And it looks like it's going to be negative 2x plus 2, also equal to 0. And from that, I'll get a couple of solutions. I guess I really only get one solution, right? From the y partial, x is equal to 1. And then if I plug that in to the other side, 2x minus 2 times 1 is 0. Right, plug right in over there. Nope. I'm sure someone out there has caught it already. Let me try that again. This is 2 times 1 minus 2y equals 0. There we go. Right, I got x equals 1, but it was from the y partial, but do still make sure you set the right variable equal to the number that you just said it was. I got the same result though. The other variable is also 1. Since on one side I get x equals 1, and on the other side I get y equals x, so y is also 1, meaning I've got a critical point right there. 1, 1. All right. There's the easiest couple of steps. The next part involves parameterizing my boundary curve. Let's go with parameterizing our boundary curve. Belongs to all of us right now. And this particular curve is made up of 4 parts. So I'm going to need 4 parameterizations and then 4 derivatives and 4 different places to check for critical points. So let's just get at it. I have these 2 horizontal lines and these 2 vertical lines. And I'll just start going through them. I'll have one f of, that's the line x equals 0. Nope, that's line y equals 0. X 0. And what does that look like? It's just x squared, right? So the derivative of that, f prime of x, is 2x, and it should be equal to 0. And since we're right here, let's just go ahead and get the point x equals 0, since that's our only solution there. If x is 0, I'm on the line y equals 0, so y is also 0, but I already have that point. 0, 0 is one of my boundary points, so I don't need to check it twice. Once will be enough. So let's try the process again. This time I'll look at the first green line. That's the line x equals 0, y is y. So I think this is just 2y. Meaning I get a derivative of f prime of y equals 2, and then that thing needs to be equal to 0, so I'm setting all of my derivatives equal to 0, so no critical point on that first vertical green line. Let's just go with none right here. My next spot, how about f of x2? So I'll look across that top horizontal line where y is 2. And I'll get the equation x squared plus, that looks like 4x, except it's not plus 4x, it's minus 4x. Minus 4x, there we go. And then plus 4, if I go with those terms in order. And then I can take another derivative here. F prime of x is 2x minus 4. That should be equal to 0, which means that x is 2. I'm on the line y equals 2. So no matter what value I were to solve here, my point would be blank 2. In this particular case, it's 2, 2. Which I'll mark right there. Notice that that rectangle is not drawn to scale. That'll be fine. And finally, I've got one more curve to parameterize. It's the one on the right. F of 3y is 9 minus 6y plus 2y. And again, I want that equal to 0. Nope, that's not quite right. Off to a real strong start today. F prime of y, which is negative 4, that thing should be equal to 0, right? Don't set it equal to 0 until you've taken a derivative. Yep. Great job, me. So again, we got our derivative. Negative 4 equals 0 comes up with no solutions. So I'll just write a none there and call it a day. Cool. So those are all of my boundary curves, my boundary points. I'll just leave it as is. Again, I think the roughest part of these problems is all of the boundary parameterizations because we have to do it a lot. But I came up with only one additional critical point. Hi. Gotcha. So my boundary parameterization I can see in each of these cases, they're just lines of the rectangle. So all of those are straight lines. So vertical lines have the equation x equals whatever. In our particular case, they're x equals 0 and x equals 3. And that came from this part right up here, defining my rectangle as between 0 and 3 for x and between 0 and 2 for y. So the extension of that, the two blue lines, the ones that are horizontal, those are y equals 0 and y equals 2, respectively. So then all I'm doing for my parameterizations is replacing either x or y with the constant number that they're equal to on those straight lines. Cool. Yeah, solid question. I think I forgot to mention that. Right, we've got 6 points altogether. So come to where I've got more space and start writing them all down. F of 1, 1. F of 2, 2. F of 0, 0. Let's go 3 at a time. I just have to plug all of these back into the function, which I've just barely got it at the top of the screen with the first one on there. This looks like 1 squared is 1, minus 2 plus 2. Altogether, that's 1. Maybe I'll just rewrite the function right here. F of xy is x squared minus 2xy plus 2y. There we go. Plug in 2. This looks like 2 squared is 4. 2 times 2 times 2 is 8. Plus 4 again. That comes out to 0. And plugging in 0 for everything. 0 minus 0 plus 0 is 0. Slide you a little bit over there. This point was on the blue line. That point was on an orange line. Those are one of my boundary points. Then I've got a few more points to go. F of, how about, let's go in order. 3, 0, F of 0, 2, and then F of 3, 2. Amount of whispering's a little alarming. No one's pointed anything out yet, so I'm assuming I'm okay. Unless. What's up?
I'm just gonna guess and say.
My colors were wrong. Wait, they were wrong? It's supposed to be green instead of orange. Oh, maybe. So 0, 0 really lies on two of the, it's like a point on one of the curves and it's a boundary point. So I went with orange for a boundary point because I got those first. But you're right. This could have been either, I think that could have been either orange or blue because it kind of fit on both. Maybe I should have put the X value in blue, but it's too late now. We've come too far. So let me go get those other points. If I plug in 3, 0, I'm going to get 9. If I plug in 0, 2, I think I'm just going to get 4. And if I plug in 3, 2, I will get 9 minus. 3 times 2 is 6, times 2 again is 12. Is that a plus 4? Altogether, that's 1. Do I get no negative values? Kind of looks like maybe I don't. All right, well, among these, I just have to go pick the biggest one to be my maximum. That's this guy. Yeah. That new eraser trick really doesn't work that well. Cool. There's a maximum. And then my minimum is the smallest among these points. I said my minimum is the smallest among these points. There we go. That'll do. So I get those minimums. Two, both along the boundary. Hi.
How did you put Y value? Two, two.
How do I get the y value for the 2, 2 point? So if I come back to this boundary curve equation, which is where I got the x value of 2, I am on the curve y equals 2. So no matter what value I got for x there, y was always going to be 2. Yeah, so really I should be plugging it back into the boundary equation. There just wasn't anything to plug in on this problem because our curve was so simple. I think we'll see in the next example that there's something more interesting to plug into. So I'll move on to that. Okay, what do we have next? Finding the absolute maximum and minimum values of the function, that guy, that's on the triangular region, bounded by and including the line y equals 9 minus x, and in the first quadrant. So let's draw ourselves a triangular region. I want it to be equal. Nope, isosceles. So maybe let's make it a little bigger, a little bigger. Okay, cool. We'll put it there. And and I've got this line, which is at y equals 0. I'll have this green line, which is going to be x equals 0. And a new line, I'll draw it in magenta. It'll be y equals 9 minus x. So that's my region. It has 3 boundary points, which I will continue marking in orange. They are 0, 0, 9, 0, and 0, 9. Cool. So when I get to step 2, that's what I'll have to start checking. I'll have 3 different parameterizations, so 3 different boundary curves to check. Oh boy. But before I get to there, let's go look at some partial derivatives. I need an x partial. It looks like it is 2 minus 2x. And again, I want that thing equal to 0. I need a y partial, which looks like it's 2 minus 2y. Again, set it equal to 0. Solve each of those equations. And by solve each of those equations, I really mean solve the system of equations. Because we should be solving systems here. It's just that the last couple of systems we've looked at have been rather straightforward. This one even more so than the last. I just solve each of them directly to get x equals 1 and y equals 1. And the last one, I at least had to substitute from one into the other to figure out my second value. But this one, just got my 2 solutions straight up. So I've got a critical point at 1, 1. Just like last time. So I'll mark it there on my diagram. You might be getting the sense that drawing some pictures on these problems will be pretty helpful. So I'd recommend it when you're doing your own work. This kind of helps you keep track of stuff. But all right, we did the easy steps. So now we have to go parameterize all of that stuff over there. Let's start with the easy two, which are going to be the blue and the green lines. So I guess I was doing blue first, so let's keep that trend up. F of, this will be x0 is 2 plus 2x plus 0 minus x squared minus 0. And then I'll go get a derivative of that. F prime of x is, looks like 2 minus 2x equals 0. So x is equal to 1. Again, just like last time. Except this time I'm on that blue line. So my critical point is at 1, 0 this time. Slide that out of the way. This is 1, 0. Up a little more space. I can see I'm going to need that out of the way too. So I've got one critical point along the blue boundary line. I'll go get the green line next. This is f of 0y. Since that green line is x equals 0, and it looks like it's the equation 2 plus 0 plus 2y minus 0 plus y squared. So a derivative of that will look like f prime of y is equal to 2 minus 2y equals 0. And I get the solution, y equals 1. Kind of a lot of symmetry going on in this problem. And again, I am stuck to the green line this time. So I'm going to get the point right here at 0, 1. Hi.
-2y, you had plus.
Well, yep. Should have been minus y squared, right? Yeah. Yeah, so I just copied the problem down wrong, but held the right information in my head. Yeah. Oops. But yeah, definitely should have been a minus y squared there. Then I've only got the last part to go. Looks like I'll have just some space below these guys. So let's try writing it in there. F of, this is going to be x, 9 minus x, which will be the equation 2 plus 2x plus 2 times 9 minus x squared minus 9 minus x squared. All right, so I'll just replace all of my y's with 9 minus x. That's what my equation told me to do. And then I'll get a derivative of that. F prime of just x looks like this. 2 minus 2. All right, the derivative of that next piece through will be just -1, 2 times -1. Maybe I should just write that out instead of skipping all those steps. Plus 2 times -1. There it is. Minus 2x minus 2 times 9 minus x times -1. And all that should be equal to 0. That's the thing I want to try to solve. And if we simplify a bunch of the chaos that's here, let's see. I'll get 2 minus 2 is 0. I'm going to have a minus 2x right here. And then let's see. Negative 2 times 9 is negative 18 times another negative 1 becomes plus 18. And then negative 2 times negative x times negative 1 is minus 2x. That 18 looks kind of awful, so let me rewrite it. 18, there we go. All of that equal to 0, which I believe gets me the solution x equals 9 over 2. Right, since that'll be 4x equals 18, then 18 over 4 is 9/2. Now, to substitute that thing, y is equal to 9 minus 9 over 2, which is itself 9 over 2. Hey, now. Come over here. This new update is just so intuitive. Anyway, I'm gonna substitute right over there. Which means I am looking at this point right about there-ish at 9 over 2, 9 over 2. When in full screen mode, I don't get the time anymore either. So that's lovely. Okay, from here, what do we want to start doing? I have, count them, 1, 2, 3, 4, 5, 6, 7 test points. So I'm just gonna start plugging them all in and hoping for the best. Those points were 1, 1, 1, 0, 0, 1, and 9/2, 9/2. And I'll just start by getting these points. 1, 1 is going to be 2 plus 2 plus 2 minus 1 minus 1. And that is a number. I think it's 4. Sure. Someone let me know if I whiffed on that. F of 1, 0 looks like 2 plus 2 plus 0 minus 1 minus 0, which is 3. 0, 1, 2 plus 0 plus 2 minus 0 minus 1. I did it again. Minus 1 again is 3. And if I'm looking at 9/2, 9/2, let's see, this would be 2 plus. This 2 plus 9 plus 9, probably? 2x plus 2y? 9 plus 9? Minus, on the other side, I'm going to get 9 over 2 squared twice. So minus 2 times 81 over 4. Let's just call it that. Minus 2 times 81 over 4. Which is going to come out to a number. 9 plus 9 plus 2 is 20. 81 over 4 times 2 is just 81 over 2. 20 is 40 over 2. So that's 40 minus 81 is negative 41 over 2. If my real quick arithmetic yields any results. Then I should go get the other values. F of my boundary points, 0, 0, 9, 0, and 0, 9. These ones look relatively easy. 2 plus 0 plus 0 minus 0 is 2. If I've got 9, 0, this will be 2 plus 18 minus 9 squared is 81. So that's 81 minus 20 is negative 61. And I'll get the same thing at the other boundary point. So now I just have to look at everything that's left over and pick out my maximums and minimums. 4 is the biggest number I can find, so it's the max. Negative 61 is the smallest number, so it's the min. Zoom out to just kind of look at the problem one more time. All the way through. All right. So I think we've got one more to go. So far, our boundaries have been mostly just straight lines. So this last one, we'll look at something that isn't that. Actually, hold up 1 second. I do just want to come like talk about maybe the answer I would have expected from this problem. If I can relate some of this stuff back to topics we've already looked at, I know what kind of shape I have from the beginning. That from section 12.6 is an elliptic paraboloid. Realized I was going to need an and there halfway through my sentence. Right, that thing's an elliptic paraboloid. It's z equals a bunch of stuff. Z is a linear term. I've got 2 square terms for x and for y. If I complete squares there, this thing sort of looks like it's the equation of a circle. In particular, it's a circle that's centered at 1, 1, and it's opening down. So again, elliptic paraboloid with more of a vertex at 1, 1. Since again, I know it's opening down, I would expect to see my maximum at that vertex, which is what we found. Maximum was at 1, 1. And then I think that my z value is just going to get more and more negative the further I am from the center. Since it's going to be related to negative x squared minus y squared. Should remind us an awful lot of a minus r squared right there. So I'm just looking for the points that are furthest from 1, 1, which happen to occur on the boundary. And since that straight line is closer than a curved arc, the critical point along that line was not further away than either of the endpoints. But maybe just, some words to motivate the answer that we found. But I digress. Let's go look at this last problem. So consider this new function, 2x squared minus y squared plus 6y on the disk. X squared plus y squared is less than or equal to 16. So let's just draw ourselves a circle. Hey, look, first try. And bad. Yeah, roughly. It's centered. Oh, it sure is. Okay, back to the problem. Okay. Finding the critical points of this function. They are at f partial x is 4x. That ought to be equal to 0. And my y partial is negative 2y plus 6. That should also be 0. And again, some straightforward solutions. X equals 0, y equals 3. I've got the point 0, 3. So I'll go plot that over here. Let me actually just make this whole thing a little bit bigger. Because I've got the space. 0, 3 is right there. So that's critical point number the first. Now, we have to parameterize that boundary curve. It looks like a circle. So sine and cosine are probably going to be the way to go. That'll totally work. I can parameterize the thing. It'll take the next 10 minutes, and we don't have that because we're running out of time. And there's actually a slightly better parameterization we can use here. So I'm going to show you that trick right away and say, this is a spot where you can look up the other parameterization. I need to come up with the boundary curve. The boundary of this function is x squared plus y squared equals 16. Right, the region itself is the inequality, less than or equal to 16, but the boundary curve is the part where it's equal to 16. And I don't have any linear x terms in my function. I just have x squared minus y squared minus 6y, which means I could just replace x squared with 16 minus y squared. So if I come back here and try to look at my function, which is going to be f of just y, it's going to be 16 minus y squared. Nope. Minus y squared plus 6y, which I could rewrite to be, don't forget the 2 that was there, 32 minus 2y squared minus y squared will be minus 3y squared plus 6y. All right, so I can just replace the x squared with the 16 minus y squared instead of doing a sine and a cosine parameterization. Either one will work, but don't forget to put bounds on your y value because y is the only variable that survived into the boundary function. Y is the variable that needs boundaries. Y is the variable that needs its bounds. So y needs to be in the interval -4 to 4. So the two boundary points I should be looking at are at the top and the bottom of my circle. 0, 4, and 0, -4. Because I was able to completely parameterize my boundary curve with just the y variable, I don't need to check the left or the right endpoints of the circle. I could anyway, just to be safe, but I won't need to. But now that I've got the boundary curve, I can go take its derivative. F prime of y is -6y plus 6. It's equal to 0, so y is 1, giving me the result x squared is equal to 16 minus 1 squared. So x will be plus or minus the square root of 15. So if I come back up and plot those 2 points, they are right there and right there at root 15, 1 and negative root 15, 1. And let me just jump ahead here real quick. To look at a spot where I've already got all of that math worked out. I plugged in those points, and here's what I found. I found the minimum was at the lower boundary point at 0, 4. I forgot to color code these. I don't know. Lower boundary point was at 0, 4. We're pointing at -40. My maximum ended up being at the critical point I found on the boundary. It was symmetric, so it was the same value in both spots at 35. And also, I said that I could have parameterized this thing with sines and cosines, but it ends up being a bit messier. So why I opted for the other one. But parameterizations are not unique. You can find lots of different ones that work. So this solution also comes up with the same answers. I get angled solutions of pi/2 and 3pi/2, which again gives me those same 2 boundary points. Very cool. That's it for me. I will see you guys again on Wednesday. Okay, bye, 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 bye. Hey, come back here.